Okay, I think we'll make a start then. So first session this morning is going to be about OpenMP optimization, but a lot of what I've said is going to apply to other multi-threading APIs as well. Yeah, if you're using POSIX threads or C++ threads, then a lot of what I've got to say is going to apply to that as well. And then later on today, we've also got sessions on vectorization and optimizing for the memory system. There's a reasonable amount of material, so see how we get on with this talk. I might start some of the vectorization material this morning. Okay. So if you've done any OpenMP or multi-threaded programming development, then you've maybe found yourself in this situation. You've written the program, you checked it gave the right answers, so you run some initial timing tests, and well, speed up was not what you hoped for. Well, what you most of us probably been here at some point if you've done any development with OpenMP. So where's your performance gone? What's happened? Why aren't you getting good speed up? So the way I like to think about it is, and the way I encourage you to think about it is, well, it's disappeared into some form of overhead somehow. So your cores are busy or not busy doing something which isn't contributing to calculating the solution. So the way I'm going to talk about this is to break down the possible sources of overhead, to try and identify all the possible things that can go wrong, and suggest what things that you might be able to do to fix them or improve them. So I like to think of it as there's really 6 main sources or main categories of overhead that we get from OpenMP programs. So there they are there. So we've got sequential code, idle threads, synchronization, scheduling, communication, and hardware resource contention. So I'm going to spend a bit of time talking about each of those. And so my title of my slide says 6.5. So what's the half? So there is another minor one which I'll mention at the end, which is to do with compiler optimization or non-optimization, to be more specific. So okay, let's have a look at each of those and talk about what they are and what we can do about it. So the first one's very straightforward, which is sequential code. So in OpenMP, all the code that's outside of parallel regions or inside a parallel region and in a master or a single directive is essentially sequential code that's being executed by only one of the threads. And the time that you spend in sequential code will limit performance. That's just a simple statement of Amdahl's law. So for example, if the code that accounts for 20% of the original execution time is not parallelized, then I'm never going to get more than 5 times speed up from that code. So if that's the problem, well, it's essentially that we haven't really finished the job. Okay, there is still a significant amount of code that isn't parallelized, so we need to go away and think about ways of parallelizing it. Now that may or may not be straightforward. There may be good reasons why there are dependencies that don't let you parallelize. But essentially, if we're spending a lot of time, a significant amount of time in sequential code, then we have to find ways to parallelize it. There's really nothing more to it than that. The second problem we can have is idle threads. So this is essentially where some threads finish a piece of computation before others and have to wait for others to catch up. Or there's other possibilities as well, which we'll come on to. But the most common one in OpenMP is finding threads sitting idle in a barrier, for example, at the end of a parallel loop or a parallel region. So this diagram is meant to be like a profiling trace. So showing the activity of 4 threads with time running from left to right. And the blue bit is meant to represent actual computation. And the red part is idle time. So in this case, the 3rd thread takes longer than the others. They all reach a barrier at the end of, say, a parallel loop or a parallel region. OpenMP has implicit barriers at those points. So all the other threads have to sit there doing nothing while they're waiting for the 3rd thread to finish what it's doing. So this is just a straightforward load imbalance problem. So what can you do about load imbalance? Well, if it's a parallel loop, then OpenMP offers us all the different scheduling options and choice of chunk sizes and so on. And you can use schedule runtime to experiment without recompiling. So you can, if you specify schedule runtime on the loop, then you can set the schedule as an environment variable. So if you want to experiment with lots of different, say, schedule kinds, static, dynamic, guided, and different chunk sizes, that's just a convenient mechanism so that you can run lots of tests without having to rebuild your code. If we have very irregular computations, then using OpenMP tasks can be helpful, particularly if we have nested parallelism and unbalanced nested parallelism. Then using nested tasks can be a good solution to that, rather than using nested parallel regions or nested parallel loops. When we use OpenMP tasks, it's essentially just describing all the available parallelism to the runtime, and the runtime is supposed to take care of the load balancing for us. Most implementations do quite a good job of that, though you have to be aware that there is some additional overhead with using tasks compared to, say, using a dynamic loop schedule, and it won't work very well if your tasks are too small. The point to note that if we do find we have a load imbalance, then so looking at the code and wondering where it comes from, it's not necessarily always safe to assume that 2 threads doing the same number of computations will take the same amount of time. So even if all our threads appear to be doing exactly the same computation, so we've got a parallel loop where every iteration does the same thing, and you use a static schedule, does that necessarily balance the load? And the answer is no, because the time taken to load and store the data may be different from different threads, depending on if or where that data is currently cached. So, and that's something you can't tell just by looking at the code, is which memory references are going to result in cache misses or cache hits. So you can sometimes see load imbalance that's actually caused by cache behavior rather than different amounts of computation. Another place where we can get idle threads, for example, is critical sections. And so if we have a block of code which only 1 thread at a time is allowed to execute, so for in OpenMP, that might be critical regions or atomics, or if we use lock routines to do mutual exclusion, then we say, for example, here, and again, we've got a timeline. So the green stripy piece of computation is a critical section, which only 1 thread at a time can execute. So, for example, if all the threads arrive at that block of code at the same time, then one of them will get in and execute it, and the other ones have to wait their turn. So there'll be some there will be some idle time as threads are blocked, waiting for entry to the critical section, or waiting to acquire a lock, for example. What can we do about it? Well, we can try and, in this case, if we can try and minimize the time spent in the critical section. So we can really go after heavy optimization, sequential optimization of the code that's inside the critical section to try and minimize the amount of time that's spent in it. In OpenMP, critical regions, we use a critical directive. That's effectively a global lock. And so all threads mutually exclude with each other on the critical region. If we actually have different pieces of data we want to protect, it's possible to use critical directives with different names. So you can add, there's an optional name you can add to an OpenMP critical directive, and only critical directives with the same name will mutually exclude. If it's possible to use atomics, then you really should, because that allows a lot more optimization. It's most implementations, it's significantly cheaper than a critical section, and it also allows things, for example, like allows if the thing on the left-hand side that's being modified in an atomic update is an array element, then using atomics allows concurrent updates to different array elements, whereas using critical is just a lock, so that mutually excludes from all of the updates. Or there might be situations where we might use multiple locks. For example, if the update is so atomics are really only applicable to a single statement update to a basic type, and not all codes meet that pattern, but you might end up using, for example, an array of locks, or associating if we have objects or structures, perhaps including a lock in an object or a structure, and using that to do the exclusion on a per structure basis. Okay, so that's idle threads. So the next one is synchronization. So every time we synchronize threads, there is some overhead, even if the threads are never idle. So example thinking about again is the implicit barriers at the end of OpenMP parallel regions and parallel loops. Even if all the threads really do arrive at the barrier at exactly the same time, there is still some cost in actually executing the barrier, because the threads have to communicate somehow, and the communication is all happening through reads and writes in the memory system. And OpenMP particularly encourages this style of programming, which is full of implicit barriers, and they're surprisingly expensive. As we'll see later on, perhaps, but obviously depends on the number of threads, depends on the runtime, the hardware, but we're looking at thousands to tens of thousands of clock cycles would be typical. So on current machines, maybe looking at tens of microseconds for a barrier. That might not seem very much, but if there's not very much work inside our loop, then that can easily dominate and prevent any speed up at all. And the other synchronization constructs are not free either, so they all cost something. And also, you can also think about creating and executing tasks as requiring some synchronization as well. So what can we do here? How do we avoid synchronization overheads? Well, clearly, some synchronization is always going to be necessary for correct execution and avoiding race conditions. But we should really think about perhaps parallelizing at the outermost level possible. If we have a choice of different levels at which we can exploit parallelism, then we should try and go for the outer ones, because that probably means we have to synchronize less often. So that's that is a way of minimizing the frequency of barriers. And depending on the code, in order to be able to do that, that may require you to reorder loops and possibly also array indices as well. It is possible to get rid of the implicit barrier at the end of a parallel loop in OpenMP with the no wait clause, but you really do have to be careful. It's all too easy to introduce race conditions by removing barriers that are actually required for correct code. As I say, atomics may have less overhead than critical or locks. I say it's not guaranteed, but in most implementations, that's definitely true. Okay, these days that atomics are much more efficiently implemented than criticals or locks. Okay, any questions so far? Okay, so the next possible cause of overhead is scheduling. So if we program in a way where we're creating computational tasks and then relying on the runtime to assign those to threads in some way, then we're going to incur some overheads. And some of that may actually be the internal synchronization inside the runtime. So there's a slight blurring here, to be honest, as to whether it's the runtime is executing some code, but it's also having to synchronize threads internally as well. Where is this likely to happen, though? It's for the non-static loop schedule, so guided or dynamic, or when we use task constructs. So if we do something like this, if we have a loop with a lot of iterations, and maybe each iteration doesn't do very much computation, and we put a schedule clause, a dynamic schedule clause with a chunk size of 1. So that means we're basically doing a first come, first served schedule where every thread just picks up one iteration, exits it, and then comes back and takes the next available iteration. There's a lot of overhead, or can be a lot of overhead in that, and that may not end up well. The message really here is that if we need to get the granularity of the tasks right. And so because if we have too few very large tasks, then we will likely end up in a situation where we have idle threads, because we can't, there isn't enough parallelism available to balance the load. On the other hand, if we have lots of tiny tasks, then we will tend to drown in the overheads of creating and scheduling them. So there's usually some optimal value for, if you like, for the size of the tasks that there may actually be a reasonable. Hopefully, there's actually a reasonable range of optimal values where it works well. But we need to think about that. So for loops, then it's really just down to a choice of choosing making sensible choices of the chunk size. If we're programming with OpenMP tasks, then it might be a bit more complicated to might need to do some blocking or combining what are the natural tasks in the application, into combining them together into chunks of tasks, and making that into an OpenMP task in order to get the granularity, in order to increase the granularity. Okay, the next one. So all of those are relatively straightforward things to think about. Now we come on to one that's actually more difficult. It's more difficult in the sense that it's a little bit harder to understand, but it's also very much harder to diagnose. We'll actually explain why that is in a moment. Okay, so on shared memory systems, the communication is effectively disguised. Okay, we don't have any explicit communication between threads. We're not sending messages between threads. So if threads are communicating values with each other, that appears as increased memory access costs, because it takes longer to access data that's either in main memory or in another processor's cache than it does to access it from the local cache. And we have to remember that on modern hardware, memory accesses are expensive. So we're talking of the order of 100 or clock cycles for main memory access. Can be more. Okay, I think AMD ROMs is like 200 or something like that. And that's expensive compared to the cost of floating point operations. So the communication between processors or between cores is taking place via the cache coherency mechanism, which we'll talk about a little bit more in a moment. But it's very different from message passing. If we have a message passing program, we can just inspect the code and we know exactly where the communication's happening. Now, the only place communication happens in an MPI code is when we make calls to the MPI library. So that's easy, and that also makes it quite straightforward for profiling tools to instrument. They can instrument the message passing calls, and they can tell you, how long each call took, and how long the message transfer took, and how many bytes were sent, and give you a lot of information. But in shared memory, the communication is very fine-grained. It's at the level of the individual memory accesses, and it's spread throughout the program in the way that's difficult to see. You can't just look at a piece of code and say, okay, I know for sure that that this load will result in a level 3 cache miss or a coherency miss or something like that. Caching mechanism is too complicated to essentially, in almost all cases, it's too complicated to try and sort of simulate in your mind, if you like. So that means that the communication overheads are much harder to analyze or monitor successfully in shared memory programs. Okay, so yeah, cache coherency is quite complicated, but from at a very high level, this is what we need to understand about it. So in one slide, try to explain cache coherency mechanism. The basic idea here is that there can only be one valid value for any piece of data in the system, despite the fact that there could be multiple copies of it in multiple different caches. So in order to preserve the shared memory programming model, the program can only ever observe one value in a memory location at a given time, despite all these copies being around in the hardware. And the way this works is that if a thread writes a data item, it will get an exclusive copy of that data in its local cache. So that becomes the single up-to-date copy. And then any copies of that data item in other caches will be marked as invalid. so to avoid any other threads reading out of date values. And then if other threads want to access that item again, either a read or a write, they must get that data from wherever that exclusive copy now is. And that takes time because it requires moving data from one cache to another in the system. So that's that's a very highly simplified description. Clearly, it's reality is a lot more complicated, but that's sufficient for us to reason about the behavior of programs adequately in general. So that leads us on to the idea of data affinity. So obviously, the way caches work is that data will be cached on the processors or in the caches next to the cores, which are accessing it. So we have to reuse our cache data as much as possible. So we'll talk about caches more in sequential context later on today. But this idea is really just an extension of that, is that want to reuse data. So in a parallel multi-threaded context, we need to write code with good data affinity. Essentially ensure that the same thread accesses the same subset of program data as much as possible. Also want to try and make those subsets relatively large, contiguous chunks of data. For reasons which I'll come on to in a minute. We don't want very fine-grained interleaving of accesses in address space from different threads. It's also another important consideration is to prevent threads migrating between cores while the code is running. Because if the operating system decides to move a thread from one core to another, that means that all the data that thread had recently accessed is now in the wrong cache. And it's in the cache where it used to be, on the core where it used to be executing. And if that thread keeps on using that data, all that it has to then move into the be moved across into the cache where it's now executing. So it's important to prevent threads migrating, in other words, to bind the threads to cores. On large HPC systems, that is normally taken care for you by the batch system. But in other scenarios, and it depends on how your batch system is being configured, that may not necessarily be true. So it's worth knowing about the OpenMP, for example. The OpenMP has an environment variable called OMP proc bind, and setting that equals to true will encourage the operating system to bind threads to cores and not migrate them around while the application is running. As I say, with a good batch setup, then you don't need this stuff. That the batch system is doing the binding for you. But it does vary between systems, so you need to check whether how your batch system's been set up and whether it's doing thread binding. Okay, so here's an example where things might go wrong with data affinity. And so what we've got here is two sets of loops. So and both of them are parallelized with an OpenMP parallel forward directive. So I want to focus on the second loop first, yeah. Because this is, as far as the outer loop's concerned here, this is badly balanced, and that's because the inner loop bounds are j equals 0, j less than I. Okay, so the bound of the the length of the J loop depends on the value of I. So this is it's a triangular iteration space. So in order to balance this loop correctly or reasonably well, we would need to take care of the scheduling somehow. Okay, so maybe we do some experiments and we find that a static schedule with a chunk size of 16 here is appropriate and gives us good load balance. But then let's look back at the first loop. So the second loop reads values from this array A, this two-dimensional array A. And the first loop writes values into A, but this is not a triangular loop. This is a rectangular loop, so J runs from 0 up to N. So this loop is well balanced, so there's no, at first sight, there's no reason not to use a static schedule and just divide the iterations equally between threads. But then let's think about the access patterns to this two-dimensional array. Okay? Because we are choosing a different schedule for the two loops, means that the thread which accesses AIJ in this loop is most of the time, at least, not the same thread that wrote it here. Okay, so this will require some communication in order to resolve these loads here. And typically, these loads will result in cache coherency misses because the up-to-date value of the data which was written here is in some other cache. So in this case, there's a straightforward solution. We could just apply the same schedule to the first loop as we have for the second one, and then we get matched access patterns to A. But that's a bit of a simplistic example. In reality, it can be more difficult to arrange than that. And another example is this one. So suppose we have a parallel loop which accesses, where the ith iteration accesses the ith element of an array A. So we execute a parallel loop. We then have a sequential loop that writes some new values into A, and then we repeat the first parallel loop again, which reads A. So when we execute the first loop, what that will mean is that we will get copies of different parts of A spread across multiple caches where the multiple threads are executing. When the master thread executes this sequentially, it will get exclusive copies of all the elements of A. So that basically gathers A, the valid copies of A all get gathered into one cache, and all the other copies in other caches will be invalidated. And then again, when we come to execute the parallel loop again, and everything again, the elements of A are in the wrong place in terms of where they're cached. So we'll end up with more misses here to resolve. So what we actually see here is perhaps a slightly unexpected phenomenon. So partly why I introduced this example is that if we measure the execution time of this sequential loop here, it will be longer if there are multiple threads executing the parallel loops because of the cost of the invalidations. So that's kind of maybe a little bit unexpected, is that these communication effects can affect sequential code as well as parallel code. which is possibly a little bit non-intuitive at first sight. So what we tend to see here, is the sequential code will take longer because of the invalidations, and the second parallel region will scale badly because of the additional cache misses. So from a point of view of data affinity, you may end up, you might have decided or basically not bothered to parallelize that loop in the middle because it didn't take very much time in the sequential code, but that can have a significant impact on the scalability of other parallel loops. Okay, so that's just a straightforward, well, relatively straightforward cache affinity. Then we have to think about NUMA effects. So this is like doubly evil, if you like. So whenever we have multi-socket systems, or indeed newer architectures like the AMD Rome, which actually has multiple NUMA domains within a single socket, then as soon as we're in that situation, the location of data in main memory becomes important. And OpenMP itself, as an API, doesn't have any support for controlling that. Okay, so there's no way to use OpenMP directives to specify where your data structures are going to live with respect to the NUMA domains. Well, that's more or less true. Recent versions of OpenMP have added support for memory allocators, so you can basically, if you have a NUMA-aware memory allocation library, then you can use it. Okay, there is the kind of semi-portable ways of using that through OpenMP, but you don't have sort of direct control. The problem here is that the common default policy for the operating system is to place the data, okay, on the processor, by which I mean in the NUMA domain, where the first access to it comes from. So the first time a core reads or writes a memory location in the application, then it will be allocated, or the OS will try to allocate that data in the NUMA domain where the access came from. So the so-called first touch policy. And for OpenMP programs, that can be the worst possible option. It's a very sensible policy for sequential code. It's a very sensible policy for MPI applications where every process has its own data. So you want the data allocated where the MPI process is running. But for OpenMP programs, if your data is initialized in the master thread, it will all get allocated into one socket or NUMA domain. And then having all the other threads accessing the data on that same socket becomes a bottleneck. You're effectively restricting your available memory bandwidth to a single NUMA domain. What can you do about it? Well, depending on in some OSs, well, particularly in Linux, you can change the default policy. You can change the policy from first touch to round robin, for example, by using the NUMA CTL command. But probably the most portable or powerful way of doing it is to actually make use of the first touch policy indirectly by parallelizing your data initialization. Okay. It may not seem, that might not seem at all worthwhile in view of the insignificant time it takes in the sequential code. Your data release citation may take a second or two, and your code's going to run for going to run for tens of hours. So why bother parallelizing your data initialization? It's because that is when the location of that data in the memory system is determined, and it's worth doing. You don't necessarily have to get the distribution exactly right, and what is exactly right may not be actually obvious unless you have very regular data structures and very regular access patterns from different threads. But usually, at least some distribution is usually better than none at all. We really just want to avoid this situation where we end up with all our data in a single NUMA domain. And then just remember that the allocation is being done on an OS page basis, okay, which is kind of order of kilobytes, unless you use large pages. So this is a potential problem with using large pages. If you go to sort of megabyte size page, then the allocation is being done in whole pages. So if your data structures are order of megabytes and you use large pages, you can't actually distribute them. The next problem we can come across is false sharing. So I've marked this as very, very evil. I should probably tone that down a bit, because modern hardware designs, modern cache designs have actually reduced the impact of this compared with some older chips. So it's still a problem, but it's not quite as bad a problem as it used to be, I would say. And the problem here is that when we think about these cache coherency operations that are being done to keep the view of memory coherent, then these are the cache lines, the cache blocks. And so these are typically 64 or 128 bytes, but they're always bigger than a word. Okay, so words of data are typically 4 or 8 bytes, depending on whether they're single, double precision, or ints or longs or whatever. But the coherency operations are always done on blocks of data which are bigger than a word, contain several words. So that means that if we have a situation where we have different threads writing to neighboring words in memory, that can cause cache invalidations. So there's no actual race condition here, because logically the threads are not accessing the same word of data, but because they're next to each other in memory, they will still cause the entire cache block to be invalidated and then subsequently refetched. And it's still a problem. If all threads are reading, that's fine. But if at least one thread is writing and the other's reading, then we've still got a problem. So the worst cases will happen where we have different threads repeatedly writing neighboring array elements. That's kind of the situation where you would sort of maybe the alarm bell here should ring if you ever if you find yourself writing code like that. Okay, so for example, if we want to have so if we have some shared array where we're counting something that happens on every thread and index that with the thread number and do frequent increments to that, then that's exactly the sort of situation, because we have, again, we've got different threads writing neighboring array elements which are next to each other in memory. You can also get problems, with loops if we use a small chunk size, for example. So if we say static 1 on this loop, so threads get alternating values of execute alternating values of I, or interleaved values of I, and then I is used to index an array, you can find that, that's a problem. In this case, how this will show up is that if you experiment with different chunk sizes, you'll find that one is not optimal, and that you have to go to a larger chunk size so that you have so your threads are writing to different cache blocks instead of the same one. So you'll find that the optimal chunk size is not 1. It's maybe, depends on the word size, but it might be, the optimal chunk size might be like 8 or 16 instead of 1. So Radimas, does the fault sharing lead to excessive cache misses? Yes, it does. Okay, and so yes, you could potentially, you should be able to observe that with hardware counters. Should be able to see that happening. The problem is it's just difficult to, you can't distinguish between cache misses caused by fault sharing and cache misses which are genuinely needed for the threads to communicate data. The hardware counters can't, as far as the hardware is concerned, it's all just the same. So your hardware counters won't distinguish them. But if you do see unexpectedly large cache misses, and depending on the system, you might be able to say, well, these are, you might be able, the hardware might distinguish coherency misses. So if you see hardware counters, large numbers of coherency misses in your hardware counters, then this is one thing you might want to look for. Okay, so any other questions about the caching, coherency, communication, NUMA stuff? Okay, so the last of my 6 categories is hardware resource contention. And this is, well, it's caused because the design of hardware is, is basically, there's some cost versus performance trade-offs going on in the hardware design. But it means that there are shared resources which, if all cores try to access them at the same time, don't scale. Okay. Or you can think about it, this is one of these things you can think about it, it's a glass half empty, glass half full kind of dilemma. You can think of it the other way is that an application running on a single core can access more than its fair share of resources. But in particular, the cores, the ones we probably most care about, so the cores and therefore the OpenN3 threads that are running on the cores can contend for memory bandwidth, and it's probably the big one, cache capacity in shared caches, and also functional units if we're using simultaneous multi-threading. So memory bandwidth is the big one. So codes which are, the bottom line here says codes which are very memory bandwidth hungry are not going to scale linearly on most shared memory hardware. What can you do about it? Well, it's really just a question of trying to reduce the bandwidth demands by improving locality, and hence increasing the amount of reuse of cache data. That should benefit that's a sequential optimization as well. I think it's going to hopefully benefit our sequential performance, but even more so when we think about the contention from multiple threads. Okay, so here's an example from ARCHER2. So this is looking at the AMD Rome processor, and we're just focusing on just using a single NUMA region. Okay, so just going up to 16 cores, all on the same NUMA region. So there's no NUMA effects in play here. So just remember, we've got level 1 and level 2 caches per core, and then we have this 16 megabyte shared L3 cache for every set of 4 cores. And using the Cray compiler, we're basically measuring the speed up for this parallel loop. So this is basically a simple parallel loop which just computes the sum of the elements in an array. Okay, so the accesses to sum are not relevant for here. Okay, they are. So, and if you're not familiar with OpenMP, basically what's happening here is the reduction clause is making private copies for each thread here, and then adding them up together at the end. And basically, the cost of that is fairly minimal compared with everything else that's going on. So really, we're just looking at the read bandwidth to this array A here. And then, so what the experiment is doing is say, okay, let's choose different values of n here, so the length of the loop, and therefore the amount of data that's being accessed in A. So vary that, and measure the speed up that we get for different numbers of threads. Okay. And so the other important thing to mention is what I did was to run the loop first. Okay, so that brings the whatever data is going to sit in the caches into the caches, and then do the measurement. Okay, so this is so basically ignoring any cold miss effects here. So basically measuring the performance in the situation where if the data can be cached at some level, then it already is. Okay, this is a little bit of a busy graph, but so let me explain what's going on here. So what I'm plotting here is the obtained speed up for that loop against the essentially the value of n, the number of loop iterations here, and that also determines the amount of data that's being accessed. Okay, so then I plot a different line for 2, 4, 8, and 16 threads. What can you see? Okay, so for small values of n, we see that we actually get significant slowdown. The speed up is much less than 1. Okay, what's going on here? Well, this is this is death by synchronization. Okay, the overhead of executing the parallel region is bigger than the cost of executing the loop sequentially. So if we draw a line across from 1 here, you can see that we actually need somewhere, depending on the number of threads, but we need somewhere between 50,000 and maybe sort of 200,000 iterations in order to break even. So that's maybe surprisingly big, but this loop vectorizes perfectly, and so you can get essentially generate as many. You can basically saturate the floating point units with this loop. So basically, the loop iteration is equivalent to data size. Yeah. Okay. So you have to. They are. These were doubles. So if you multiply by 8, you get the data size here. So for 2 threads at least, okay, so once we've overcome the overheads of the parallel region, we basically hit a speed up of 2 for all large data sizes. So that's fairly straightforward. It's kind of what to expect. We go to 4 threads. We actually do just about attain a speed up of 4 for one particular data size, but then it dropped slightly to a value of about 3 and a bit. Okay. And in this region, the data fits into the level 3 cache, and all those 4 threads, the way the threads are bound to the cores means that all those 4 threads are all sharing that same level 3 cache. So the reason that I don't get a speed up of 4 here is because of the contention for the bandwidth to the level 3 cache. And as I make the data size bigger, eventually it doesn't fit in L3 cache anymore, and out to accessing main memory, and the speed up drops down to a value which is only just about 2. Okay, so 4 threads, if I'm hammering main memory bandwidth, only get a speed up of about 2. And for 8 threads, see some similar increase, and never these kind of data sizes never actually reach a value of 8, and then you get this very big spike here for this particular window of data sizes here, and that's because now I'm running 8 threads on 8 cores. I now have access to twice as much level 3 cache. So this particular data size here, on one thread, I was essentially not able to use, the data is too big to effectively use the L3 cache. On 8 threads, because I've doubled the L3 capacity, then the data does fit in the L3 cache. This is why I get this superlinear speed up spike here. But then as soon as I exceed the capacity of the 2 L3 caches, then we drop back down to accessing main memory. And again, we see not much more than 2 times speed up. And then we see something fairly similar for 16 threads as well. Okay, we also see this. So in this case, we actually the spike is slightly broader because we've now got 4 L3 caches to utilize rather than just 2. But apart from that, again, eventually we run out of L3 cache to use, and we end up with something like 2.5 times speed up. So if we are hammering the main memory bandwidth, then, and we're inside one NUMA domain, then we really, we're very much limited by the hardware, by the resource contention for the memory bandwidth here. And this is particularly marked on this architecture. So on other processors, this effect is not as marked. So Rowdy asks, after this part, would it help to spread threads? Yes, it would. Okay, so if I spread those threads across more NUMA domains, then yeah, it would give me also more L3 cache, but it would also give me more memory bandwidth, because if I use 2 NUMA domains, then I would double the available memory bandwidth, and I would spread the threads across those as well. So absolutely, yes. If I go outside a NUMA domain and I underpopulate, so spread threads across NUMA domains, then absolutely would be able to get access to more memory bandwidth. But in this scenario, I'm just constrained to what's available from one NUMA domain. Yeah, so this effect is particularly marked on this AMD Rome architecture. So I mean, again, you can think of it the other way around. You think that it's basically a single thread is able to access almost half of the available bandwidth from the NUMA domain. and then but then adding more threads, which are all also consuming the memory bandwidth, then you saturate it very quickly. You can almost saturate the memory bandwidth with 2 threads. So Christian says, suppose this multiple times. Yeah, absolutely. So as try to explain, I basically ran it. It is run multiple times, and I'm ignoring the first time through. So I'm ignoring the cold cache misses. So the reuse is coming from repeated execution. You're absolutely right. Okay, so we've also seen a bit of this other effect here, is that where cores have some shared cache, again you might see that code not appear to scale well because a single core is able to access the whole of the shared cache. Radim asks, is it possible to enable cache bypassing for just a block of code in the case of single data usage? I think the answer to that is essentially no. Okay, unless you go to assembler intrinsics. Yeah, but you'd have to program the assembly. It's in general not, as far as I know, it's in general not possible to persuade the compiler to do that. So you need to code it in. You need to code your own assembler to do that. Oh, okay, that's interesting. Okay, might be some support for that in the AMD compilers. So one possible complication here is that if you are doing cache block tuning, if you're doing cache blocking for reuse, so you need to think about, beware of tuning block sizes for a single thread, and then running multi-threaded code, because in that case, then every thread is going to try and will have the wrong block size, because it thinks it has available. You've tuned the block size as though you had access to the whole cache, or you might have tuned the block size as though assuming you had access to the whole cache, and when you run multiple threads, you don't. Last one, hardware threads. Yeah, so if we use hardware threads, SMT, hyperthreading, whatever you like to call it, and then threads running on the same core will have to share their functional units, so particularly the floating point units, as well as the cache space and memory bandwidth. And for a lot of codes, using hardware threads doesn't actually help. benefits tend to come where threads are idle because they're waiting on memory references. So this is, code with, with very unfriendly memory access patterns, non-contiguous or, sort of random-looking memory access access patterns. Okay, so Neil asks, does each thread, I guess, work on a different core? Yeah, you'll see. Yeah, you would see exactly the same thing with MPI here. Yeah, you'd see so provided you did the binding in the same way. So if you ran, say, 4 MPI processes all on the same, all sharing the same L3 cache, and then went to 8 across 2 L3 caches, you would see the same superlinear speed up. Yeah. Yeah. It's not actually kind of specific to having threads running. You could see exactly the same thing with an MPI implementation of that. Typically, codes which are very bandwidth hungry or which saturate floating point units. So, for example, if we're doing dense linear algebra, may not benefit from hardware threads because we're already because a single hardware thread is already maxing out the whatever shared resource it is. And typically, it might also run slower because in order to exploit the hardware threads, you had to explicitly expose more parallelism in your application. So you had to double the number of OpenMP threads or double the number of MPI processes, and then that will have an impact in terms of other parallel overheads like synchronization or load imbalance or communication. So very often you find that with a lot of applications, hardware threads are just don't help because of this trade-off, and that's why a lot of HPC installations basically disable it, or at least default to not using more than one hardware thread per core. So it's usually possible to override that if you really want to, but the default is often set up so that you don't use them. And then, of course, the other way you can contend for hardware resources is by oversubscribing them. So, running more threads than you have hardware execution units, so be that cores or hardware threads, is generally a bad idea, because then the operating system has to try to give each thread a fair share of the cores, and then we're into context switching. So the cost of stopping one thread and starting another is high. It's into the thousands or tens of thousands of clock cycles, and it also ruins your data locality because you've got one thread running on a core, filling up the caches with its data. Then that thread gets stopped. Start another thread running, and none of the data that it's wanted is currently in the cache. So this is also generally a bad idea, or at least the reason why running more threads than you have hardware resources is almost certainly never going to help. Sometimes you can see it appearing to help, particularly on in an environment like a laptop or a desktop system. It appears you do get additional speed up from having running. If I've got 4 hardware cores, my code will speed up, or may speed up a little bit more by using, say, 8 or 16 threads. But that's really because you're influencing the operating system to give your application more resource, compared with all the other processes that are running. So you can observe the kind of the opposite trend here in a kind of in an environment where there are lots of other processes running, because running 16 threads, will sort of try to encourage the operating system to give more resource to your code. But in general, on HPC systems with dedicated nodes, so then it's not going to help. Okay, so I mentioned the 6.5 reason, and this is compiler non-optimization, and this thankfully happens very rarely, but it's just worth being aware of it in case you get unlucky. Is that very occasionally adding OpenMP directives can inhibit the compiler from performing some sequential optimizations. And the symptom that you see here is that if you run the parallel code on one thread, that has a significantly longer execution time than the sequential code. So if that's happening, then it may be because something has gone wrong with the sequential optimization. It's very hard in general to find a workaround to this. And I say, thankfully, it's rare. If it does happen, it can be very difficult to figure out why. Sometimes it can do some of the things to try and help the compiler do its analysis, like making shared data private or making locals. Adrian talked a bit about yesterday. Making local copies of variables, making local copies of global variables and things like that can sometimes help. But in general, it's pretty hard to diagnose what went wrong or which part of the compiler's analysis has suddenly failed because you added an OpenMP directive. And I've seen odd things happen. An example, I've seen one with a Fortran code. And it had a slightly odd idiom that it was passing arrays through subroutine arguments, but instead of just passing the name of the array, it was explicitly passing the first element of a multidimensional array. So in Fortran, those are entirely equivalent things to do, but for some reason that affected the compiler optimization, and it made just adding the OpenMP directives running on one thread made it run about twice as slow. So you can get weird things like that. So Random asks, is the one thread code really the do parallel code path? Is there a sequential code path? In OpenMP, if you run the parallel code on one thread, you really are running the parallel code path. Yeah. Because there are some what happens with in order to interpret the OpenMP directives, the compiler is doing some does some code restructuring very early on in the compilation phase. So what it actually does is if you have an OpenMP parallel loop or parallel region, what the compiler is doing is extracting the code inside the block of code inside the parallel region into an internal function, and that's how the implementation is really done. So the code, so you actually are creating, the compiler is creating new functions, and it does things like so private variables become local variables inside that created function, and so on. So yes, it really is executing different code than the sequential code if you've compiled with OpenMP. There's also other, even if you have no parallel directives in your code, then adding the OpenMP flag does actually change the compilation process a bit as well, because it forces all local variables to be stack allocated. So you can see nasty things like just turning on the OpenMP flag causes you to run out of stack space, for example. That is possible. But the one thread, there's often like a one thread code path internally, so the runtime tries to avoid a lot of the overheads of parallel regions if there's only one thread. So it can skip over an awful lot of internal code if there's only one thread. So the overhead of a parallel region on one thread is like 2 orders of magnitude less than it is on 2 threads. Okay, so what can we do about this in a kind of process context? So what do you do if your code's giving you poor speed up? Well, obviously, so I guess most of you are probably quite experienced developers, and you know perfectly well what to do. But the way I like to think about it is, what we need to do is to make progress here is to try and classify and localize the sources of overheads. So in other words, which of those problems that I've mentioned is the problem, and where is it happening in the code? So if we can do that, then we have a reasonable chance of being able to direct some optimization and fix it. So yeah, so in some sense that's no different from sequential optimization at some level. But think about, okay, so what's the problem? Where in the code is it happening? Use tools to help you. Timers, hardware counters, profiling tools. And obviously, usual thing, fix the big problems first. So, and as I mentioned in the chat yesterday, so standard profilers, things like gprof or the profilers you get in IDEs, can be pretty confusing for OpenMP code, because what you see is a profile where they accumulate the time spent in functions across all the threads. So that's not necessarily terribly helpful. It tells you something, so it's not completely useless information, but it makes it quite hard to interpret, and you can't see, for example, it's very difficult to see where you've got load imbalance, where some threads are spending longer in one function than the other, because effectively all that you're seeing is a total or an average. You can get a lot out of using timers. You can use OpenMP's built-in timer, add timers around every parallel region, and also around the whole code, or at least the main computational part of the code that you're interested in. So that at least allows you to work out which parallel regions have the worst speed up, and also say, don't necessarily assume that because of the memory effects which I talked about, don't assume that the time spent outside parallel regions is fixed. It might not be. So it is worth measuring that as well. So if you've got the time for the whole code and the time for every parallel region, then you can subtract one for the other. You can work out the time spent in sequential code by subtraction. So discussed a bit yesterday, there are various performance tools available, all of which do something fairly useful, or reasonably useful for OpenMP codes. One of the problems I've found is that some profiling tools don't adequately account for idle time. Okay, and see that it's hard to get a good handle on thread idle time from some of these tools, and different tools report it in, either report it or don't report it, if threads are idle doing nothing in between parallel regions, does that show up in your profile? And the answer is maybe, and it can show up as some incomprehensible internal runtime function, or it might just not show up at all. If the threads have actually gone to sleep between parallel regions, then you won't see anything. I quite like, I don't have very extensive experience with all of these tools. I quite like Scholastica when it works. For this, you can do tracing experiments with Scholastica, and that does make some attempt to break down the overheads into different categories in a kind of similar way. The problem with almost all of these tools is that they tell you nothing about or tell you very little about the memory system behavior. Yes, you can get hardware counters, but they don't tell you how much time you spent communicating between threads, or they don't tell you how much time did you lose because of memory bandwidth contention. If you're just dealing with pure open code, then this tool at the bottom here, the Power Tools Thread Spotter, is quite interesting. It does something different from conventional tools. So what it does is it actually takes a statistical sample of all the memory accesses in the application, and then replays that through a cache simulator. So it's cheaper than doing a full it's not doesn't have to do a full memory trace. So it just takes a statistical sample of the memory accesses and then tries to replay that through a cache simulator. So that can tell you things like bandwidth contention and false sharing and so on. So that's quite an interesting tool. So Radim said, with bandwidth contention, if the community observe peak bandwidth or low bandwidth. So what you will typically see is that the achieved memory bandwidth is quite high. Okay, if bandwidth contention is going to be a problem, it means it must be because your threads are consuming a lot of memory bandwidth. So you would see you will see high bandwidth. It's just that bandwidth can already be saturated by small numbers of threads. So the reason you don't get speed up is because using, say, in the case of the AMD Rome, just using 2 threads per NUMA region, you've already soaked up almost all the available memory bandwidth, and adding more threads won't give you any more performance benefit. Okay, so there is, okay. So if you want to play around with profiling and working with an OpenMP code, there is one in the set of exercises. I say, please just do whatever don't feel you have to work through them all or work through them in order. Please just pick and choose whatever's interesting for you. Okay, so well, that's taken us up to 11 o'clock UK time. So let's take a break now, and I'll be back in half an hour to support you through sessions up until lunchtime.